So when the transistors are off, at that point of time, what happens is there is some current which is still flowing in my circuit. And what are these currents? Subthreshold current. We know that when VGS is less than VT, or the threshold voltage, ideally my current should fall to 0, but it does not drop linearly but drops down exponentially, and it is a function of the threshold voltage. It clearly shows that as my threshold voltage reduces, my subthreshold current increases exponentially. Here is a formula which we have already seen when we studied subthreshold current. Reverse bias leakage current. Now this is nothing but, when we again saw this in the previous clips, that when we draw the cross-sectional view of a CMOS circuit, we find that between the diffusion and the substrate, or the diffusion and the well, there are reverse bias diodes which are formed, and this reverse bias diodes will also constitute to a reverse bias current, and that is nothing but given by ID equal to the formula is written. Again, we have seen this in details when we studied reverse bias leakage current through the PN junction diodes. And the last one was gate tunneling. We saw this as one of the drawback of scaling. We saw that though SiO2 is a very good insulator, electrons can tunnel to gate through SiO2 if the gate oxide thickness is 20 angstrom or less than that, because tunneling drops off exponentially with oxide thickness. It means that if oxide thickness is high, tunneling is low, and vice versa. So all these three constitute to static power dissipation. Because P static, now we know that there is no supply current, right? Because we saw that in case of CMOS inverter or in CMOS circuit, that there is no direct path from supply current to go to ground, and there is no direct path from VDD to ground. So that current was 0 in quiescent condition. We saw that. So now this P static is nothing but I static into VDD, and I static is nothing but leakage currents, which is nothing but either subthreshold or reverse bias or gate tunneling. Ideally, it's the summation of all three of them. Now a question might arise is there any way in which we can try to reduce this static power dissipation? If you look on your screen, the equations will give you a hint, and we'll go into the elementaries of it. We are not going to go into the nitty-gritties or detailed part of reduction of static power. We'll just see it superficially. So one of the ways through your equation here you can make out is, if you reduce your VGS, then probably your subthreshold current would decrease. Similar is the case if you reduce your VDS. And one other technique is if you increase your threshold voltage. But if you increase your threshold voltage, what will happen is the transistor will take long time to turn on. That means technically the speed of my circuit will reduce and the delay will increase. So increasing the threshold voltage is not a very good idea right now with the look of things. We can try to reduce our gate to source voltage, and we can try to reduce our drain to source voltage. And we can also lower our temperature. If our temperatures are lowered, the thermal voltage can be also taken into consideration, which will help us in reducing the subthreshold current. So we just saw that as threshold voltage, if we try to increase the threshold voltage, then my transistor will take a longer time to turn on, which will reduce the speed of my circuit, and in turn will increase the delay. However, there might be some transistors in my circuit where delay does not matter. So in those transistors, we can definitely increase the threshold voltage, and we can do that through a phenomena called as body effect, in which my substrate or my body and my source are not connected to the same potential, which leads to the increase in the threshold voltage. So we can do that for certain transistors in which the speed or the delay is not very critical, or they are not in the critical path. This technique which we are using is nothing but multiple threshold CMOS circuit or empty CMOS circuit, where certain transistors will have a low threshold voltage, certain will have a high threshold voltage, which will help us in the reduction of subthreshold current. Another technique which we can go ahead and do is, we should not try to reduce our thickness oxide below this value, so that we can prevent gate tunneling to happen. So these are some of the basics. I can show you the circuits also, how this is achieved, but that's currently beyond the scope. So I think you have understood what is static power dissipation, what constitutes to static power dissipation, and we saw some of the basics on how static power dissipation can be reduced. In the next clip, we will see about dynamic power dissipation, and the combination of both of them will lead to the total power dissipation in case of your CMOS. Hope you have followed. Stay tuned and thank you very much.